Hi you guys, today we're going to talk about the periodic table and the periodic law. Before we begin, make sure you have your highlighters and lots of colored pencils or colored pens today, and don't forget to print out your periodic table from Canvas. And it should look something like this because we're going to use it and we're going to mark it all up, and I'm going to show you how to read it today based on where the trends are on this periodic table. Okay, so let's get started. Okay, so the history of the periodic table. So in the very first periodic table was made in 1869 by a Russian chemist, Dmitry Mendeleev, and his was the very first published, or one of the first published periodic tables. Mendeleev's periodic table was based on two properties, and those two properties were based on the atomic weight and the chemical properties of elements. And his periodic table was the chemical properties part of it was based on something called valence, the valence number. So the valence number is actually the number of electrons in the outer shell of an atom. So what that really means, and why is this so important, the valence number, is because these electrons that are in the outer shell are the ones that are involved in a chemical reaction. And I'm going to label reaction as RXN. So Mendeleev's periodic table was used for quite a while until the 1900s, where people started becoming very dissatisfied with his periodic table. And that's because they started discovering more isotopes and the presence of isotopes, and they wanted to incorporate that into the periodic table. So in 1913, a British chemist by the name of Henry Moseley came along, and he started doing studies on different elements, and eventually he found out that his study led to the discovery of the atomic number. Atomic number, and the atomic number, as you know, is the number of protons in the nucleus. So this is really important because Henry Moseley is the guy that we now use his concept, or his periodic table, and it is the modern periodic table. So he's the guy that's responsible for it, the modern periodic table. So his periodic table, or the modern periodic table, is actually organized into two principles. The elements are arranged by a successively higher atomic number, and the columns are arranged so that the elements have the same electron configuration, the same arrangement of electrons in the outermost energy level. So what does that really mean? That means that he actually used, where it says the same arrangement of electrons, he's actually talking about the valence number. And that's why it's so important. So he's talking about the valence number, or the electrons in the most outer shell. So periodicity. The modern periodic table is arranged so elements are in rows in order of increasing atomic number. And so the columns contain elements with similar properties. And because of this arrangement, there are patterns of elements' physical and chemical properties. And these patterns are called trends. The trend, so what does a trend mean? A trend means that a particular property has a general pattern of increasing or decreasing along a row or a column. So in your periodic table, the existence of these patterns and trends are called periodicity. So if you look at your periodic table real quick, I'll show you just a segment of it, a portion of it. Notice that there are columns that you have in your periodic table, and you have rows in your periodic table. And notice that your periodic table is actually set up where the atomic number is increasing each time. Okay, so, and this is the pattern that the pattern can actually be seen on the periodic table. Okay, so if we move on to the next page, we have valence electrons. Move it down so that you can see it. Okay, so valence electrons, and we've been talking a lot about valence electrons. Valence electrons are electrons that are located in the outermost energy level, and these are, and write this down, but these electrons are very important because these electrons are the ones that are involved in a chemical reaction. And don't you forget that. Can't emphasize that enough, how important valence electrons are. We'll talk about the Lewis dot structure in a minute. I'm going to talk about the periodic table and then I'll come back to it. But let's talk about the octet rule. So the octet rule is when elements react, they will either gain, lose, or share electrons in order to achieve a lower energy level state. And for the most part, this is where they're the most stable number of electrons, is when an element's outer energy level has 8 electrons in it. So understand this, you guys, that 8 is a very important number, that an element can have a maximum of 8 valence electrons, and that's why we call it the octet rule. Remember that the word octet means 8. So that's really important. It can have a maximum of 8. Doesn't mean that it has to have 8, but it's just a maximum of 8 valence electrons. So understand that when these electrons, when they're involved in a chemical reaction, when a chemical reaction occurs, these electrons are the ones that become ions. Okay, so remember that they are the ones that become ions. And moving on with the periodic table, you have your representative elements on your periodic table. Okay, so the representative elements, they're groups 1 through, and I'm going to write this down because your periodic table is a little different, but in your periodic table, they're really groups 1 through 2, and then it's 13 through, 13 through 18 on your periodic table. Okay, and why are these representative elements so important? Is because these elements are most stable when they have 8 electrons in their outer shell. They will either gain or lose electrons, okay, the smallest possible number of electrons, in order to achieve that octet rule, which is 8 electrons in their outer shell. So you have, on the periodic table, you have groups or families, and these are actually the columns that are going up and down on your periodic table. The alkali metals are in group 1, and they have a +1 charge. These elements are a soft metal, but they're a good conductor of heat and electricity. And most of all, they're extremely reactive. They're highly reactive. The alkaline earth metals, which is in group 2, have a 2+ charge, and they're also reactive, but they're not as reactive as the alkali metals. Then you have your boron group, and your boron group has 3+ charge. You have your carbon group. Your carbon group has 4 and then 4+, so it's 4- and 4+ charge. Your nitrogen group is now has a 3- charge, and your chalcogen group has a 2- charge. Your halogens group has a 1- charge. And these are also, you guys, they're the most reactive nonmetals that are around. Your noble gases are they're unreactive, and so they don't even have a charge at all, and they're extremely stable. Your transition metals, they're metallic properties, and they have more than one charge, but they're all positive charge. Your intertransition metals, see, pull it up if you can see that. Your intertransition metals, which are also called the rare earth metals, are your lanthanides and your actinide elements. Okay? And really, your intertransition metals are really the same as your transition. They're the same as transition metals. Okay? Keep in mind, you guys, that when I say, when I'm talking about metals, I'm talking about cations, that they are a positive charge. When I'm talking about nonmetals, those are anions, that they are a negative charge. So going back to your periodic table, and let's see, let me fix it a little bit. We're going to mark up this periodic table for you guys, and we're going to mark up the periodic table. We're going to write all of the charges down, where each of the groups is, what the name is of the group, and for your valence electrons. So make sure that you guys are able to, and this is where you're going to use different color pens. So we're going to go back. If you need to know how to spell it, make sure you have that your notes handy so you can spell everything correctly. So group 1, like I said, is the alkali metal. Group 2, like I said, is the alkaline earth metal. Right here in the middle is where your transition metals are. You have your boron group. You have your carbon group. You have nitrogen group. Notice that these groups are, the names are based on the first element in there. The only one that's a little different is your chalcogen group, which is really the oxygen group. Okay, so and then you have your halogens. And then you have your noble gases. Okay. You do have here in the periodic table, your intertransition metals are right here. So this is your inner transition metals. Okay, so next, so notice that this is the representative elements are group 1, 2, and then 13 through 18. Normally, if we had a different kind of periodic table, these would be listed as group A, and then the transition metals and the intertransition metals would be considered group B. or represented by the letter B next to each one of the group names. Okay, so take another color. You're going to need two different colors because we're going to talk about charges and valence electrons. So right here, make a key at the bottom where charges for me will be in green. Okay, so I will write the charges of each of the groups in green, and then the valence electrons I will write in red. So really, what is the difference between charges and valence electrons? Valence electrons are the ones that are involved in a chemical reaction. Those electrons, because those electrons are in the outer shell, they're involved in a chemical reaction. Charges are the electrons. It tells you how many individual electrons were actually involved in the reaction. So you have a lump sum of electrons in the outer shell. Not all of those valence electrons will be involved in a chemical reaction. You know which electrons will be, or you know the number of electrons based on the charges. So for example, if something has a +1 charge, that means there was only one electron that was involved in the chemical reaction. Okay, so let's start out with valence electrons. So we're going to start off with group 1. The group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13 has 3. 14 has 4. 15 has 5 valence electrons. Group 16 has 6 valence electrons. Group 17 has 7 valence electrons. Now when you get to the noble gases, helium has 2 valence electrons, and then after helium, as you're going down, you now have 8 valence electrons. Okay, so helium has 2 valence electrons, and then in the noble gases, neon and all the noble gases afterwards have 8 valence electrons. In your transition metal, you have 2 valence electrons. Okay, and in your inner transition metals, you also have 2 valence electrons. Okay, now, so as far as charges go, group 1 has a 1 plus charge. Group 2 has a 2 plus charge. Group 13 has a 3 plus charge. Group 14 now has a 4, but it's a plus and minus charge. So you want to write here a plus and minus. And let me zoom in so you can see what I am doing. So notice that I wrote plus and minus right here. So group 15 now will be a 3 minus. So that changes a little bit now. Group 16 will be 2 minus. Group 17 will be 1 minus. And then your noble gases, well, those are going to be a total of 0 charge, okay? Because they're very stable. Going back to your transition metals, your transition metals have a variable charge. So they have more than 1 charge usually, and that we will tell you, you will have to memorize some of these, but we'll tell you what those are when the time comes. And then your inner transition metals right here, well, your inner transition metals, we're going to write on the other side, also have a variable charge. Okay, they also have a variable charge. So really, this is your periodic table that you have. Let me zoom out again. Okay, and this is how your periodic table should look. If I were you, I would keep this in a very safe place. Put it in a sheet protector so that you have access to it and nothing happens. The charges and the valence electrons are really very important for you to know them. So start learning them and memorizing them. Okay? But moving on, going back to your notes to talk about the electron dot structure. So don't put away the periodic table yet, because we are going to come back to it because we need it for the valence for the Lewis dot structure. Okay, so going back to this, what is a Lewis dot structure? This shows symbols. It shows the valence electrons with dots that are surrounding the element. And your valence electrons will never exceed the number 8. Why? Because that's the maximum you can have in the octet rule. You have a maximum of 8 valence electrons. So I'm going to write here, you have I'm going to write in red to keep up with your periodic table. Maximum number of valence electron. Okay? So, and each one of those valence electrons is represented by a dot in the Lewis dot structure. So there is a notation that you need to follow for the Lewis dot structure. Okay? So the first notation is, let's say that you have the element X. Okay? And you you only have 1 or maybe 2 valence electrons. Well, there is a certain notation for it. So since each valence electron is represented by a dot, the first dot would be written right there, and then the second dot would be written right there. And I'm actually denoting that with numbers right now, but we'll do some with actual dots. Then a second type of notation that you have is, let's say you have element X, and now you have more than 2 valence electrons. Okay, so how would you show the valence electrons around this element? So the very first valence electron will be written on top. The second one, this is where it differs from where it's just a maximum of one, where it just has 1 or 2 valence electrons. The second one will be written right here, number 2. Number 3, the fourth dot would go right there. The fifth dot would go back up on the top, the sixth dot, the seventh dot, and then the last or 8th dot would be written right there. Okay, so let's do some examples. Let's write the Lewis dot structure for lithium. So if you look at lithium in your periodic table, lithium is in group 1, and it has 1 valence electron. So you would write the valence electron right here, because it's valence electrons. Each valence electron is donated as a dot. That's where number 1 goes, right here. Then our second example is beryllium. Okay, so we have beryllium right here. It's in group 2, and it has 2 valence electrons. Okay, so we're still going to use this model, the first valence electron and then the second one. So first and then the second valence electron. We have boron is our next example. Boron is in group 13, and it has 3 valence electrons. So now we're going to use this model right here. So we're going to have 1, 2, 3 valence electrons. So 1, 2, 3 valence electrons. We have carbon. Carbon is in group 14, and it has 4 valence electrons. So we're still going to stick to this model, but it's going to be 1, 2, 3, 4. So 1, 2, 3, 4 valence electrons. You now have nitrogen from the nitrogen group, and that has 5 valence electrons. We're going to go 1, 2, 3, 4. The same as carbon, but now we've got the 5th one, so we're going to come back up here, and we're now going to pair it. So we've got oxygen is next. Oxygen has a total of 6 valence electrons. So we're going to go back, 1, 2, 3, 4, 5. And now notice number 6 is right there, so we're going to draw 6 valence electrons. We've got fluorine is the next one. Fluorine has 7 valence electrons. It is a halogen. So we're going to draw our 7 valence electrons. 2, 3, 4, 5, 6. Okay, and then 7. It's going to be right there. And then we have here neon. Neon, you guys, is a total of, it has 8 valence electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7, and then 8 valence electrons. So you can see that each valence electron is paired up in here. Let's do helium real quick. Helium is also a noble gas, but don't forget that helium has 2 valence electrons, so it's 1, 2. We can also pick one of the valence electrons from here. Let's pick chromium. If we do chromium, remember chromium is a transition metal. That means it has 2 valence electrons, and that would be 1, 2. Okay, you can do the same thing. You guys just learned about nuclear energy. So let's do uranium. Uranium is an actinide, and it has 2 valence electrons. So uranium, 1, 2. Okay. So I hope this really helped you understand how to read a periodic table, the concepts of valence electrons, and really who's responsible for it. There's a long history in chemistry with all these scientists, and each one just slowly making discoveries a little bit at a time to give us something that we now have, which is a very well organized periodic table. Okay, so thank you.